Okay, well, good morning. Happy November. This was a picture taken yesterday. The idea being that one of these students is dressed up like one of the flying pigs from the physics practical, and then some other students dressed up like other farm animals, including the TA, and so there was an entire flying farm of animals. And if you look very carefully in the background, there's also another student. Let's see if we can. Who's me, and that is the first time that has ever happened, as far as I know. The glasses, the gray hair, the button shirt, even my leather jacket, kind of thing. So it's my favorite costume. Maybe the scariest costume I've seen in a while, but my favorite. Okay. Also, so there's a final exam schedule posted now. You can go search it up or whatever, and you should look. But you can see us here. We're all over the campus. So I'm going to be wandering around through all these rooms. And it's a Saturday morning, which is kind of strange. Instead of watching cartoons, you'll be doing a physics exam. I don't know when they started Saturday exams. It was about 5 years ago. It's a thing now. Have a look at your full exam schedule. Make sure you don't have any conflicts or anything. Keep in mind that the final exams are run by the faculty registrar. They're not run by departments, so it's not me. I'm just a guest. I do, make the questions, but once they receive it, then it's out of my hands. So we don't have any control over the exam schedule, or if you have a conflict, or if you petition something, miss it, or something like that, you got to contact them. I can kind of give you their phone number, but that's all I can do. What's everybody doing? By the way, there's candy up here as well as the mic if you ever want free candy. I'm going to keep bringing that to my office hours until I run out. It was the stuff I didn't give away last night. So, okay. You say, so this was an office hour question I had on Monday, that the limit, it's talking about this equation for gravitational potential energy, and I mentioned that this has an arbitrary 0 point of 0 when r goes to infinity, because I think 1 over infinity is 0, I guess, or the limit of 1 over x as x approaches infinity equals 0. So, what about the limit as r goes to 0? Students ask me that. Shouldn't then u sub g go to negative infinity? So that was a really good question. I had to think about that. And it is true that mathematically, with this equation that we got here, if you said r equals 0, this does diverge to negative infinity. But in reality, you can't do that. So this equation applies for objects, real-sized objects that can be modeled as homogeneous spheres, really. And the distance is the distance, the distance between the centers of those two objects. So you can't cause the centers of two spheres to be 0 distance apart from each other, right? They would crash. They'd physically crash into each other. So in real life, you can never have u sub g go to negative infinity. It's a really good point, though. Okay. What other good things? There was also, someone asked about this escape speed. Isn't it proportional to mass? So, no. The little m there is the mass of the planet, like Earth or something. So there's two m's in these equations, m1 and m2. One of them is the mass of this big, huge planet, and the other is the mass of the object. And the mass of the object canceled when I did the escape speed. And again, this only works really if the object that's escaping is much less massive than the planet itself. There's all little addendums to some of these equations and for them to really work. Another great point, this is from the pre-class survey, somebody mentioned that in chemistry, work done by the system is negative work. And they were confused about those conventions. So in this textbook, it is the same convention, I think. Like if you look at this she calls it a generalized work energy principle from chapter 7, it goes E initial plus W equals E final. So if you think about what that means, W is the work done on the system. If W is a positive number, then it means the final energy is greater than the initial energy, so that you've added energy to the system. So it's called doing work on the system. So it's the same as chemistry. I think they carefully set it up that way so there wouldn't be confusion. There are texts that do it the other way. But here, if a system is doing work on its environment, then it's going to lose energy. E final would be less than E initial, and the W would be negative in that case. Negative work done on the system is the same as the system doing work on the environment. Okay. So, but really good that you brought that up. Someone asked, how do we take a rest? I cannot rest in university, so you gotta rest. I do hear you completely, but you kind of almost, when you're really busy, you gotta almost put it on your schedule, like rest time. Like actually add it to your schedule. I found when I was a student, I still find these days that it's not physically that I need a rest, it's mentally. It's sitting there in front of my laptop or something that you can only do that for so long, and you need to shift gears somehow. For me, a lot of times that's actually involves exercise. But yeah, so next week, obviously, there's the reading week, and the purpose of that is to give you guys some rest. So definitely take a couple days off, please. What did Obi-Wan Kenobi tell Luke Skywalker when he was having trouble with his wrench? Use the torque, Luke. That was this morning. Again, thanks for that. Nice little Star Wars joke. Okay. So, chapters 8 and 9 are all about rotation. And someone asked about what was going on with these extended bodies. Basic idea is we had that whole point-like object approximation from chapter 2. And in that case, what was happening, you have a small thing. What matters is the forces on that object. And the only thing that matters about the forces is the magnitude and the direction of the force. But now, it also matters where on the object you apply the force. This is sort of a third thing. So that's extended bodies. They're not points, but they have some shape and size. So, and that's when you get torque and things that can rotate. So you have to draw what's called an extended force diagram or extended body force diagram, where you just draw like a picture of the object as usually a rectangle or a circle or something, and then you draw the forces, same as you did before, acting on that object, but now you should draw them where they are applied. Okay, we'll talk a lot about that. Torque is kind of like a force. It has different units, but it's what gets objects rotating. It tries to rotate an object. And rotating means you can spin or roll around an axis of rotation. So here's a rigid body model for an extended object. You can imagine these people standing still because the gravitational torque is kind of above the base. We assume that the object has non-zero size, but the distances between all the, atoms or something and all their orientation is the same, so it doesn't change its shape much when there's forces applied. And I'm just going to quickly introduce a couple of conventions for us. Okay, so imagine a particle like maybe this orange piece of tape, and it's rotating, so it can go around like that. Or I don't know what it is. It's traveling in a circular path around an axis of rotation, or around the center of circular motion. So so r is the distance from the center of the circle out to the object, and you can call the origin, the rotation axis, and then you can put y as up and x is to the right. So if you want to keep track of the position of that object, you can use theta, where theta is measured from the x-axis counterclockwise. And then there's also something called path length. How far does the object move if it changes its angle by like a delta theta? And that'll be s. S is this arc length, which turns out to be r times theta if you measure theta in radians. So you can imagine if it goes the whole 360 degrees around, it'll go 2 pi r arc length. And that's 2 pi radians, so that's how that works. Make yourself comfortable. Okay. And then what you do is there's this, whoops. Yeah, sorry, there it is. That's what I want. Vt. This is the tangential speed. Remember that? They had that t-axis we were talking about before. So this is the tangential speed. And there's this new variable called omega. It's not. It looks like a W, but it's not a W. It's an omega. But you can call it W if you want. It's fine with me. But what it does is it represents the amount of angle per time that the piece of tape is going. So, for example, if it goes 2 pi radians in 1 second, then it's 2 pi radians per second. So omega is called the rotational velocity, rate of change of the rotational position theta. And then you can plug that into this equation. The speed is equal to that radius times omega. So just sort of going through some of this stuff real quickly for you. And then there's something called alpha. This would be if the thing is speeding up or slowing down. So this is tangential acceleration. It's a little different than the radial acceleration. The radial acceleration we had in the previous slide because it was just keeping it on a circular path. But this is now a sub t, the tangential acceleration, which means it's speeding up or slowing down. And this looks a little bit like an A, but it's an alpha. When you use the Greek letters, you're often talking about angles. So this means that this thing is speeding up or slowing down, and it's in radians per second squared. So meaning, like, if it starts here, and if you're speeding it up, it gets faster and faster and faster and faster and faster. Or you might be slowing it down, if you've got negative alpha. Okay. So that's that. You can make plots of these things. Let's try to do this motion. So if you start at theta equals 0, which is usually when it's on the x-axis, and then I speed it up and then slow it down and stop it. That's kind of the motion that's being shown there. So what happens is theta goes up, maybe stops, I don't know where it is at the top there, maybe it's 180 degrees, it goes around to the other side. What omega does is it becomes positive, and then it slows down and goes back to 0. And what alpha does is it's positive for a while when it's speeding up, and then it slows down, so it goes negative. But it's sort of going to be similar. We'll talk about this more, but it's a bit similar to what the linear motion was in chapter 2. You've got this velocity, or omega in this case. It's the slope of the theta versus time graph. And then the alpha is the slope of the omega versus time graph. Yes, question?
The last slide, you called it tangential speed and not velocity. Why not velocity? Does it not have a direction?
Yeah, I guess it has a direction. Yeah, you always call omega angular velocity. The direction, though, is, I guess, for omega is usually clockwise or counterclockwise. That's sort of why we're going with. Yeah, why did I call it speed? I guess this equation, r times omega, it does give the speed, right? Omega being the number of radians per second that it's going. But yeah, it would have a direction in the tangential direction. But yeah, good point. Velocity is vector. Okay. Yeah, arc length is s. The tangential, there it is. Now I'm calling it tangential. Sorry about this. Being a little sloppy with my notation. Tangential velocity, vt is equal to omega times r, and tangential acceleration is at is alpha r. And sometimes I like to kind of look at the analogy. So it's like going to Greek. So linear motion you'd call position x. If you're talking about rotational stuff, you tend to talk about theta. And then like the slope of a position versus time graph becomes either velocity or omega. And then the slope of the velocity versus time becomes acceleration, alpha. And then, so then, we're going to get into more things, which is the force is what causes something to accelerate. And you have Newton's second law, which is the acceleration is equal to the net force divided by the mass. So what we have in rotation is that you have some torque, which causes something to have angular acceleration. And the net torque divided by this new thing called I gives you the alpha, the radians per second squared. So that's the rough idea here. And this kind of concept is covering both chapters 8 and chapter 9, but I'm kind of trying to give you a bit of an overview. So some of this is, you haven't read it yet, but if it doesn't come up in chapter 8, it comes up in chapter 9. So we'll be coming back to this, but so that's an intro, which tells you a little bit about what torque is. So, when objects turn around an axis, physicists say that they undergo rotational motion. You can imagine a wheel, but you can also imagine even a door. If you think of a door, what it's really doing is it's actually rotating around a rotation axis, which is the hinge of the door. It doesn't really look like it, but that's what a door does. So in order to open a door, you have to apply a torque to it. And you can imagine different forces having different torques. So what causes rotation? There's 3 factors that affect the turning ability of the force, and these are all going to be going into the equation for torque. One is where you apply that force. The other is how much force you apply. That'll be important. And the third one is just the direction that you apply that force. All 3 of these are going to go into the equation. Let's see if I can crank up this top hat. Can you guys find top hat? I just opened it up. Consider the common experience of pushing open a door. Shown is a top view, a bird's eye view looking down upon the door. So there's the hinge and 4 different forces, F1, F2, F3, and F4, all apply to the door. So and they're all the same magnitude force, but they have different directions and they have different places on the door where you're applying the force. So which one of these would have the greatest torque, I guess, and have the greatest effectiveness of opening that door or rotating it? Please think and pair up and share. Okay. See what the survey says here. You guys got it? F1, 99%. Holy smokes. Okay, you guys kind of way ahead of me here. Great. Okay. So, well, we'll just circle that then. You guys got it. Basic idea, torque is the rotational analog of force. Force causes things to accelerate along a line. Torque causes things to have angular acceleration. So lever arm is one thing I'll talk about. I might do this a little more next class, but it's the distance between where you apply the force and the hinge or whatever, wherever it's pivoting. Putting a handle farther from the hinge increases your lever arm, so it increases the amount of torque you apply for the same force. Should we maybe try that if I put aux plate? I have a little bolt here. Actually, does someone want to tighten this for me? Someone's strong. You maybe adorn it. You want to really tighten it up so that I can't untighten. Has anyone ever over tightened like a lid or a bolt? So I want you to tighten that bolt for me as much as you can, so that you don't think I'm going to maybe this one. Sure. So just clockwise, I guess, to tighten it. Are you loosening it or tightening?
Oh wait, no, counterclockwise.
Yeah, clockwise. Yeah, there you go. Clockwise, tighty. Is it really tight? Oh, okay, good. Okay, pretty good. Let's see if I can. But the thing is, thank you very much for that. And maybe grab some candy. In case you. What? Okay. So, now let's see if I can loosen it. But I'm going to use my wrench. Okay, so that's the idea. So, that's no problem. Okay, so that's it's not that I'm strong, it's that I have a bigger torque, right? So what's going on there is that I've got two things. I've got this force and also the lever arm, how far I'm applying the force away from what I'm trying to do, which is take off this loosen the bolt. So it requires torque to loosen a bolt or to take the lid off of a jar of jam or something, and you can increase the torque, the same force, by increasing the lever arm. Okay. That's all pretty much fun. Same thing came up this morning, two forces. So if you kind of imagine again, you guys have got it. Force 1, force 2. This one will have a greater torque, right? Because it's got different values of R. This is like F1 and R1, and this is F2 and R2. Then torque of 2 is going to be greater than the torque of 1. It'll be twice as much. So there's an equation which sort of just falls out of nowhere at some point in this chapter. Okay, this is the Greek letter tau. We use a lot of Greek when we get to chapter 8 and chapter 9. But basically, when you've got some kind of axis here, and you're applying a force here, then there's this vector from the axis to the place where you're applying the force. So this is L with a little arrow on. And then theta is the angle between those two vectors. So remember, every vector has a magnitude and a direction. So if you want to find the angle between the two directions, you have to connect them tail to tail. Right? So there's your F, there's your L, and that's your theta. And then you can use this equation, F plus or minus FL sine theta. And what this plus or minus is, by convention, plus means counterclockwise torque, and minus means clockwise. At least most people use that convention. And the reason, it always seems a little weird, but I think where it's coming from is that when we measured theta in the first place, we measured it from, remember, the x-axis, and then we went kind of up towards y. And if you think about that, then theta, like something's rotating with positive omega, that's a counterclockwise rotation. So that's how I remember it. Anyway. So like for this one, in all these cases, theta equals 90 degrees for all of these. And do you know what sine of 90 degrees is? It's 1. So this is just torque is equal to F times D. because the sine theta is 1. And it's counterclockwise, so the plus comes on there. This one is going to be, the torque is going to be 2 FD. This one, the torque is going to be 2 FD. And this one, the torque is going to be 4 FD. So you guys got that? You guys got it? But what about when it's not 90 degrees? This screwed a lot of people up, so just be careful. This is like a shoulder, which is the axis. Here's like the arm, and here's this force, F. And it says that the arm is 30 degrees below the horizontal. But that's not theta, right? Because this is this thing L right there. So to find theta, you redraw L and F to connect the tails. And if you do that, you'll notice that's F down there, and L is down here, that theta is 60 degrees. Because this was the 30 over here. That's L. Okay? So the equation that you have to use here is going to be 8 times 9.8, that's the force, times the 0.55, that's this distance, from here to here, I think, equals 0.55 meters. So, and then times sine of 60 degrees, and that gives you the 37. It's a tricky one. We good though? Time's up. Doing great. Okay. From the pre-course, the survey this morning, someone said the unit of torque is newtons times meters, which seems like the unit of work and energy, joules, is the same. So that's actually, I think, true, but it's not. They're way different, and so it's probably best not to think about this. As far as I can tell, it's just a coincidence that torque and work have the same, like the base SI units. It is true, it's kilograms, and there's a meters squared and a second squared on the bottom, but torque is not a form of energy. It's it's a twisty kind of force that causes things to accelerate. So you should not think of it that way. Torque is a force that causes rotation or tries to cause rotations. The unit, we just say it's newtons times meters. Nobody ever says that the unit of torque is joules. I guess it's out of context or something, but it's still a good point. It's something interesting to think about. So it's newtons times meters, and you have a torque wrench. Sometimes it says foot-pounds on it. I've got a torque wrench here. This one says foot-pounds. But so a foot is a unit of length and a pound is a unit of force. And so that converts to torque there. But sometimes there's a specified amount of torque, like when you're screwing in spark plugs in your engine or something, you're supposed to use a torque wrench so you screw it to the right torques. Okay. Should we do an example? Let's do it. Someone up there agrees. All right. Louis uses a 20 centimeter long wrench to turn a nut. Okay. The wrench handle is tilted at 30 degrees above the horizontal. So let's draw the little nut here as a little hexagon. We'll label it nut. And the wrench handle is tilted at 30 degrees above the horizontal. So let's try to draw the wrench like that. Something like that. And you say that this is 30 degrees. All right. And Louis pulls straight down on the end with a force of 100 newtons. So this is the force. And it says calculate the torque. So let's assume, it doesn't actually say here because there was no diagram, that the wrench is to the left of the nut. Like as I've drawn it. As drawn. It's always fun when people walk in front of the projector screen. Okay. And the system here, I guess, would be this, the wrench plus the nut. So what's the torque? Well, the torque is going to be, we can kind of redraw it. There's your L or something. There's your F. We're going to define this as the axis. And if we want to use this equation 8.1, since it's in your textbook, you would say it's equal to plus or minus FL sine theta. You have to, again, redraw these vectors so that they're connected by their tails. There's F, there's L. I haven't drawn it very well, but this was 30 degrees, and here's 90 degrees. So I think theta is equal to 30 plus 90, which is equal to 120. Okay. So you should get used to doing that. And it's clockwise. Sorry, counterclockwise. The wrong way. Counterclockwise. We're going to call this positive torque. So it's just tau is equal to plus of 100 times 0.2 meters times the sine of 120 degrees. And I got plus 17 newtons times meters. Okay. Questions? Okay. Okay. So again, the sign convention for torque, if you're twisting your pencil or something in front of you, a negative torque would be when you're trying to twist it in the clockwise direction, and a positive torque is twisting it in the counterclockwise direction. So in order to figure out this, you always have to have some axis of rotation anytime you're talking about torque. Should we do a top hat? I feel like might be a image missing from your top hat, but here it is. So a ladder leans against the wall like this. The wall is to the left of the ladder in this case. What is the sign of the torque of the normal force of the wall on the ladder? Positive, negative, torque is 0, or it depends on where we choose the rotation axis to be. So think about that. Tell your neighbor what you think. Please try to click in a guess within 15 seconds. Remember, you get 80% just for participation. 10 seconds. Okay. Let's see what survey says. So a lot of people are saying negative, but 61% of you said that it depends on where you choose the rotation axis to be. So very good. So this was a trick question. And the reason that I tried to trick you here is to just emphasize this point, that torque depends on where you choose the rotation axis to be. And the ladder doesn't clearly have a hinge anywhere, like a door would or something, or it doesn't have, like a wheel clearly has an axis of rotation. It's sort of obvious where the axis is. With the ladder, it's not obvious. So don't just pick it. And if you do pick it, then you can get a sign of the torque. But I didn't pick it. Okay, so let's now pick it. So sorry about that. If you chose negative, it's not a bad idea. Okay, same question. Torque of the normal force of the wall on the ladder, but now we're going to choose the rotation axis to be at the bottom of the ladder. So repeat the same question. Okay. See what survey says. answering. So then now it's negative. Right. So this is a weird one, but remember, normal means perpendicular to a surface. So the normal force from the floor is up, but the normal force from a wall is always sideways. It's a horizontal force there. So it's, if you want to draw a little vector, it's going to the right. So now we choose the axis to be down here, axis. And now what I think to myself is, again, I try to think of it if it's a little pencil, so if this is the rotation axis, if I'm pushing it to the right, then it's going to rotate it in the clockwise direction. And clockwise is negative. So that's how I figured that out. So I always have to imagine when you've got a force being applied, if it were the only force, which way would it tend to want to rotate the object around your chosen axis? And if it's clockwise, it's negative. If it's counterclockwise, then it's positive torque. Should we do some more practice ones? Here's another one. The next one is, what about the friction? What's the sign of the torque of the static friction force on the bottom of the ladder? On the floor on the ladder. So the floor is exerting a normal force, but it's also probably exerting a static friction force. So think about what direction that is, and then think about the torque. Okay. If we have some agreement, click your final answer, please. Okay. Survey says. Okay, this is another sort of tricky one, but 75% of you got that. The torque in this case is 0. There is no direction to 0. So meaning that if I were to draw the forces here, there's going to be the normal force of the floor on the ladder, and there's going to be the static friction force, which I think is to the left of floor on ladder. So static friction is always perpendicular to the normal force, but there's two perpendicular directions. It could be to the right or it could be to the left. So it isn't really clear, but the way I think of it is that if it were a slippery floor and there were no static friction, which way would the ladder tend to want to slip? And I think it would kind of slip to the right, if you could picture that. So how does it get prevented from slipping? Now there's a static friction force to the left. So, but anyways, it doesn't matter because the axis is right here. And so L equals 0. And that means that the torque equals 0. Any force that's applied right on the rotation axis will have a 0 torque. Okay. So I'm getting you used to these things. So torque is a couple of things. It is force, it's related to force, but it's also proportional to that distance. So if there's no distance, then there's no torque, no matter how big the force is. You can't open a door by just pushing on the hinge, right? It's not going to open it. Okay. And then, so this is another one, is gravity. So people ask a lot about what's the torque due to gravity. Well, what you do is you calculate the center of mass. Any rigid body will contain a special point in which that if a force is exerted on that point, the object will not turn. So, for example, this heart-shaped thing. They talk about this in the textbook, and they imagine that you're actually pushing on the heart shape in different places. If you were to push right here, for example, in that direction, it would spin it clockwise. If you were to push it here in this direction, it would spin it counterclockwise. But if you push it here where the line goes through this point, then it just pushes it along without turning it. And so that is called the center of mass. And you can try different places, and you can find the center of mass of an object that way. And then also, if you like lift up that heart shape and try to support it underneath it, you can balance it right under the center of mass. So, when calculating the torque due to gravity, you're allowed to kind of pretend that gravity is a force which reaches up with like a hook from the center of the earth or something and hooks onto the object at its center of mass and pulls at that point. It's not quite true. Really what happens is that gravity is acting on every particle that's inside the object. But if you're just trying to calculate torque for one of these torque problems, then you can treat gravity as if it were acting at the center of mass. You get the right answer for torque. So what happens here is that the torque of gravity is as if it's pulling at the center of mass. So if you support it right underneath the center of mass, then that support point becomes kind of like your pivot, and then the torque due to gravity is 0, because it's at that, L is 0 for that. So let's go back to the ladder, and I'll ask you one more question about the ladder. What is the direction of, what's the sign of the torque of the force of gravity of the Earth on the ladder? Once again, let's define the rotation axis to be at the base of the ladder. And then after this, I'm going to give you a handy trick for calculating torque, which I think it always works for me, called lever arm, and then we'll be done. Positive, 90%, yeah, I agree with that. Reason being that the force of gravity, so what you do is you imagine that it's at the center of mass. So for a uniform object, the center of mass is just the geometrical center of the object. So it would be right here. This would be where you would draw the force of E on ladder or something, the Earth, the gravity force, which is equal to m of the ladder times g. And so what that does is, again, if this is the axis down here, again, I imagine my object is being pulled down. If it was to rotate the ladder, it would turn it counterclockwise, right? So that's a positive torque. So really good. This lever arm trick I mentioned I was going to tell you is that so the idea is that you can use the torque is equal to F times D, where D is equal to L sine theta. So what this means is that D is what I call the lever arm, is the distance between the force line and the rotation axis. The force line is the line that passes through the force. In either direction. So we know how to find the direction of a torque by thinking about which way it will twist. So the importance of this equation FL sine theta is only to find the magnitude of a torque. So what I like to do is I forget about the sine theta because I always get so confused with finding those thetas. And what I do is, for example, maybe with this, remember that wrench and the nut? And what happens if I've got this force acting down, then there's a force line here. This distance right here is D. And you can usually find that geometrically. And then you just do torque as F times D. And then you don't have to worry about the thetas at all. So that's a nice little trick for you. I'll use that in an example in next class on Friday. So keep on reading through chapter 8. Maybe when you come back, we'll have some time during quizzes. You can tell people what your plans are for the reading week. I'll see you Friday.